Great. Okay, so good morning, everybody. What I would like to talk to today is how to access superconducting ground states with a special flavor of fermionic NQS that we call hidden fermion states. And before I do anything, I would like to acknowledge my collaborators on this. Oops, I thought that was going to work. Let's see. It was working before. Okay, maybe I'll do it that way. Let me try again. Yeah, that's mine. No, doesn't work. Yeah. Is there a... Is this working?
Yeah, this should work.
Yeah, no, the pointer works, but okay, doesn't matter.
Or you can,
Okay.
you can take it off and insert it into the computer. So
Yeah, I'll do that. That's a good idea. Sorry about that. I'm just going to do it that way. Yeah. Okay. So this way people who are late can just take their seats. So just to give you some motivations, we all know that if we deal with strong quantum systems with large interactions, one of the both, I would say, challenge and opportunity that there is that we have many competing low energy states with very small energy differences between these different states. So this is obviously a challenge to computation because that means we need to resolve energy differences with exquisite accuracy. But if you take a broader view from the material science point of view, this is also an opportunity because it means that you can control these materials with small perturbations. And this is something which is used, for example, in FEMPROBE experiments to switch materials from one state to the other with relatively small perturbations. But from the computational point of view, there's no doubt that this is a real challenge. The energy differences between competing states can be as low as 1 in 1,000 of the bare energy scales, namely the hopping, let's say, in a typical Hubbard model. So this is illustrated here. It is now a very solidly established fact that the ground state of the Hubbard model, let's take the canonical 1/8 doping, for example, has stripe ordering at strong coupling, at strong enough coupling. So stripe ordering, for those who have never seen this, is something in which we have a spin density wave with a modulation which is a little bit away from the antiferromagnetic wave vector. And the holes like to accumulate at the nodes of this spin density wave, which means that we have a spin density wave with a certain wavelength, and in this canonical stripe ground state, the charge wavelength is half the spin wavelength. It doesn't always need to be like that, but this is sort of the canonical stripe phase that you find in the Hubbard model at 1/8 doping and strong coupling, let's say U over T equal 8. And what you want to understand, so this is an insulating state because we have one hole per site in the stripe. And what you want to understand is what happens when you perturb this state. And you can perturb it, for example, by introducing a next nearest neighbor hopping. There is some really nice recent work, I'll mention it at the end of the talk, that has established superconductivity when you do that. So this would be this route, increase T prime and go to a superconducting state. You can also wipe away the stripe ground state by, say, reducing U, and then you get some sort of metallic state, if you want, roughly described as a Fermi liquid. Perhaps it's not exactly a Fermi liquid, but I'm not going to address that in this talk. And what you want to know is whether that state would be also unstable to superconductivity On general grounds, we know that any Fermi liquid should be unstable to some form of superconductivity at very low temperature. That's the Cohn-Luttinger phenomenon. But you want to know, what's the size of the gap and what's the symmetry and so on and so forth. And the energy differences between these different states, again, are going to be very, very small. So this is to set the landscape and to spell out the motivations. Okay, so so this is what I want to cover in the talk. I talked about the motivations. We need very good variational wave functions, and I will say a few general things about fermionic neural quantum states. Then I will focus on one specific route that we've been pursuing, namely the hidden fermions route to neural quantum states, and our recent work taking what we did a few years ago, namely determinantal hidden fermion states, to what we are doing now, namely Pfaffian wave functions. I'll go on with benchmarks and comparisons on some models we understand better, and then the cherry on the cake at the end is about superconductivity in the Hubbard model. Okay, so that's the plan. And, this thing is going in reverse. That's very interesting. And before I do anything, I would like to acknowledge my collaborators on these projects, and especially three heroes, Javier Robledo Moreno, who was a student at NYU and CCQ, who has now transitioned to IBM for a couple of years, and Chris Roth and Ao Shen, who have really been pushing these hidden Pfaffian wave functions, and my other more senior collaborators on this topic at the beginning of the field, as well as some other kind of applications of this method. Chloe Govan-Diaye was an intern at CCQ, and Joe Tyndall is an expert at tensor network methods and DMRG, with which we made some comparisons. Okay, so a few things about neural quantum states, very general things. Everybody in the audience more or less knows that, I think. The general idea is that we can view the wave function of a many-body quantum system as a map between a very large dimensional Hilbert space and just the field of complex numbers. So this is typically the sort of thing for which a neural network might be a good way to represent that map, because it's exactly what we do when we map 2 to the n pixel picture to cats and dogs. It's not cats and dogs, but it's a complex number with a phase and an amplitude. But what the heck? And that's the basic idea, of course, behind the Carleo-Troyer paper about 10 years ago. This was originally started for spin systems, but in the last several years, we've seen a number of generalizations to fermions. And of course, the challenge there is to learn some sign, because the fermion wave functions have to preserve antisymmetry, which means that if you work in some sort of first quantized manner, you need to ensure the property here. While if you're going to think more in the second quantized way, where to each first quantized configuration, you associate a unique representant in the Fock state of occupation numbers, well, you need to keep track of the sign that connects this first quantized set of position to its representant in Fock state, that throughout this talk I'm going to call N. Okay, so fortunately, the machine doesn't do everything for us. There are some human choices that we still have to do. I don't know how long this will last, but these are, I try to itemize on this slide some of these human choices that we have to make when we design a specific form of fermionic neural quantum states. So the first thing is, of course, to start with a general ansatz for the wave function, and there are many flavors on the market. You can think of Jastro plus backflow. This is really directly inspired from several decades of work on variational Monte Carlo wave functions. You can decide to follow a different route, which is what I'm going to talk about, namely hidden fermions. There are many other flavors. You have to decide whether you're going to write your wave function basically on as a determinant or a sum of determinants, or whether we're going to use Pfaffian, etc. So there is a question of general ansatz and form of the wave function. Then, of course, you have to pick an architecture of the neural network or the different neural networks that are going to enter the parametrization of your wave function. There are many choices: transformers, CNNs, group convolutional network, etc. A key point here is about symmetries. We have learned the hard way that symmetries are absolutely essential to ensure good energies and to improve optimization in the neural quantum states. So which symmetries are you going to implement, and how costly it is to implement these symmetries? Because if you don't pay attention, these symmetries can be really costly to implement. And I'm talking about translations, but also symmetries that are not necessarily commuting, like all the internal symmetries, point group, and so on. And then finally, improving and finding the optimal optimization strategy, and that comes with, for example, fast determinant updates, min-SR, and so on and so forth. So all these choices will control many things in your results. It will control the expressivity of the wave function, the accuracy of your results, and the computational cost. Okay, so what I'm going to do now is I'm going to give you a brief intro to what we did 3 years ago, namely hidden fermion wave functions. And that's this paper. Javier Robledo Moreno was the first author of that. And this is the idea. The idea is here described in a really cartoonesque way, but it makes it very easy to understand. Imagine that plane here is my Hilbert space of all possible wave functions, right? And I'm going to highlight in blue the space of Slater determinants. So wave functions that are a single Slater determinant. Now, this plane here is actually not the physical Hilbert space, but an augmented Hilbert space. So in this cartoon, the physical Hilbert space, the one we are interested in, the configurations of your spin model or of your Hubbard model, is actually depicted as the green line. So the green line is where physics is, and we're going to enlarge that Hilbert space to the whole plane by introducing additional degrees of freedom. We'll see how to do that in the next few slides. And the idea is that it may be possible to pick a wave function here in the blue blob, which is a Slater determinant in the augmented space, which, when projected onto the physical space, becomes an entangled wave function. As you see, when projected here on the physical space, this wave function is outside the blue blob. It has entanglement and correlations, and if you want to represent it as Slater determinant, it has to be a sum of many Slater determinants. So that's the idea. And in fact, it can be proven that any quantum mechanical wave function can be brought to the form of a Slater determinant, provided you enlarge the Hilbert space to a large enough dimension, and you have a projection rule, and that's the key thing, which takes you back to the physical space. So you bring in correlations or entanglement by the projection mechanism. So loosely speaking, this idea is actually inspired, but only inspired, by what is traditionally called slave particle methods or auxiliary particle methods. For those who are not familiar with that, this is a technique that was developed for many decades, especially at the beginning of the field of heavy fermions and high TC. And the idea is the following in its most pristine form. There are many flavors again. Imagine we have a U equal infinity Hubbard model, so let's say a TJ model, where on each side we can only have 3 configurations, 0, up, or down. We're going to introduce an additional degree of freedom, a boson, which tracks the empty state. So we're going to declare that we have an enlarged Hilbert space by a bosonic degree of freedom, where when we have no electrons, we have one boson. When we have an electron, we have one fermion and no boson. But of course, if we let the boson do whatever it wants to do, that's a huge infinite dimensional local Hilbert space because boson numbers are not bounded. And what we need to do is to impose a constraint that either we have one boson or we have one fermion, right? So the total number of particles should be one on each side. And this is the projection that takes you back from this enlarged Hilbert space to the physical Hilbert space. So this is the well-known idea in the theory of correlated electron system that sort of motivated our hidden fermion construction. But as the name goes, we actually don't enlarge the Hilbert space with bosons. That would be not very practical because the Hilbert spaces are too large. We just enlarge the Hilbert space with additional fermions, hence the name hidden fermions. Okay, so let me explain how this works in details on a toy example of a two-side Hubbard model. What can be simpler? You know, it's a caricature of the hydrogen molecule, let's say. So, two-side Hubbard model, I'm going to be interested in the sector with two electrons. We know the exact ground state of this system. It's made out of placing one electron on each site on each different site with antiparallel spin. And that's that term. When U is large, of course, it is very unfavorable to place two electrons on the same site with antiparallel spin. So this coefficient here is close to 1 when U is large, and this coefficient here is close to 0 when U is large. But, of course, when U is small, the ground state is really placing two electrons with antiparallel spins into the lowest bonding state, to talk like chemists, so these two coefficients become equal, right? Okay, so the exact formula is here, and you can check that this has the proper limits. Good, and if you want, this is the crossover between placing two electrons in the bonding state to the Heitler-London strong coupling singlet limit of the hydrogen molecule. So how are we going to describe this ground state by this hidden fermion idea? So what we're going to do is, besides the physical electrons, which are these two guys, we can form these linear combinations if we want, we're going to introduce an additional fermion, which is like a flag. And this additional fermion can live in either of two quantum states, one which we call S for singly occupied here, which says I am in the singly occupied component of the wave function, and the other one which we called HD, which is doubly occupied, which is a flag for saying we have a double occupancy, right? And now we can construct a Slater determinant, which is this guy here. So this is just acting with these three operators on the vacuum. So this is Slater determinant. And when we project back that wave function onto the physical Hilbert space, so tying the configuration of the hidden fermion to the configuration of the physical electron, this projection here is telling me if we have if the hidden fermion, the single hidden fermion is in the S state, that means that we have no double occupancy, while if it is in the D state, this means that we have one double occupancy. So if you tie the occupancy of the hidden fermion to the state of the physical electrons, and this is the projection P, you can show that this Slater determinant, when projected back, is exactly the wave function you're looking for. Okay? So this is an extremely simple toy model that illustrates the idea of what we mean by enlarging the Hilbert space and then projecting back. Of course, the big advantage of this thing is that now your wave function is a single Slater determinant, so you can do everything you usually do with Slater determinant, you can update them quickly and so on and so forth. And the thing you need to do is to learn the projection from the enlarged Hilbert space to the physical Hilbert space. Okay, so to learn this projection is a little unpleasant because this is a connection between discrete numbers, right? We have a Fock state in the enlarged Hilbert space, and we want to associate it to a given Fock space in the physical Hilbert space, and neural networks are not good at learning things on discrete variables. Fortunately, we don't have to do that. What we really have to do is not to learn that projection rule, but to learn the value of the amplitudes in the Slater determinant once this projection has been found, right? So the only thing we have to learn is a bunch of entries in the Slater determinant, which are just complex numbers, right? And that is something a neural network can do. So jumping over some formalism, this is sort of the general form of our hidden fermion construction. The phi's are the n physical fermions we are interested in, and the chi's are the n tilde hidden fermions that we introduce. And to each given configuration of our physical fermions, so where the fermions are, say, on your lattice sides and with which spins, we associate one unique configuration of our hidden fermions, but what we really have to learn is only the amplitudes that enter the Slater determinant of these guys. So in the original thing we did, sorry about that, in the original thing we did, the full wave function, so if we decompose the wave function on the computational basis, which would be in the case of the Hubbard model, the position and the spins of the electrons on the different sites, right? The amplitude of the wave function is just given by a single determinant of a bunch of orbitals, and everything that has to do, so the upper block here is in the physical sector, this is the hidden sector, so there is a physical, hidden physical, hidden sector, and everything that refers to the quantum numbers of the hidden fermions was parameterized rather by a neural network. So in the original implementation that we did, sorry, I don't have a slide about, do I have a slide about that? Yes. In the original implementation that we did, all the upper block of the matrix were individual amplitudes that were variationally optimized, but all the lower rows of the matrix were actually parameterized by individual neural networks in which the input of the network is the Fock space configuration of my physical electrons, and the output of the network are the complex numbers that you want to enter into your determinant. So that's what we did originally, as you will see, and we did it with extremely simplistic architectures for the neural net, namely just a couple of layers perceptrons. As you will see in the following of the talk, we've switched to much more state-of-the-art architecture, and we also do slightly different parametrization of the wave function when we turn to Pfaffians, but this is the general idea. Okay, so a few general things about this representation. First of all, you can show that this is actually a universal representation. Any many-body fermionic state can be represented by a hidden fermion determinantal state, provided the Hilbert space is large enough. And this is a little bit like Sebenko's theorems in neural networks, or the ergodic theorem in StatMech. It's something that is nice to know, but is totally useless, because the thing doesn't tell you if you need exponentially many parameters or not. So take it as it is. You can also show that any backflow lattice wave functions, any backflow wave function on the lattice can actually be represented as a hidden fermion determinantal state. there is some loose qualitative connection between these approaches because you see that the amplitude of the wave functions that comes from the hidden fermions depend on the configuration of all the other fermions. Okay, so this is to put this in connection with other things. This is one of the early results we got in this 2022 paper that was stripe order in the Hubbard model at 1,8 doping on 4 times L cylinder. This is here L equals 16. With the older implementation of hidden fermions, it was hard to do much more than about 100 sites maybe. And what you cannot see on this tiny plot here is that the ground state energy we got on 16 times 4 cylinders was actually close to the DMRG energy, but not quite there yet. But that was very encouraging. And this was actually obtained with only a few additional hidden fermions, like 4. Sorry?
Is there any spin density here?
Yes, there is a spin density. This is the canonical stripe. Okay, so following this paper we wrote a few years ago, there's been a number of applications of these hidden fermion determinantal states. There were some very nice paper by Alessandro Lovato and co-workers on nuclear matter, extending the formalism to continuous space, low-density neutron matter, TJ models. We have a fun paper on the Mott transition between a metallic state and a non-magnetic Mott insulators. If I have time, I'll talk about this at the end. Other fully connected models, including Subir's SYK. And recently, there is a paper here you might be interested in, which establishes a systematic computational comparisons to backflow wave functions of the original hidden fermion wave functions by my colleagues in France at the Collège de France. Okay, so now I want to switch gear a little bit, and I want to go more into state-of-the-art thing, which is switching from determinants to Pfaffians. And the motivations to do that is, of course, superconductivity. There's nothing wrong with looking at superconductivity with Slater determinants, by the way. You can optimize the hidden fermion determinantal wave function in a situation where you know there is superconductivity, like negative U. And then the way to detect it is to measure the long-range behavior of the pair or the order parameter correlation function, right? And see if it asymptotes to a constant non-zero value. Even if you have a Slater determinant architecture, your wave function is going to be able to capture that. But it's not a super expressive wave functions for superconductors. It's much more natural to actually embed the idea of pair formation in the structure of the wave function itself. And that is one of the reasons we decided to switch to the Pfaffian architecture. Another reason, which is perhaps even more important on the technical side, is that, as you will see, switching to Pfaffians allows a much more efficient implementation of symmetries, and hence to go to much larger system. And now with the hidden fermion Pfaffian wave functions, Chris and Aoshen can actually simulate system with several hundred sites. Okay, so what is a Pfaffian? Well, you all know about Pfaffians. The prototypical example is the BCS wave function. It's a wave function of pairs of electrons. Okay, I can rewrite this wave function, pulling out the UKs. I can rewrite this wave function in exponentiated form. And here I've switched also to real space, but that you can also write that exponential of sum over k, fk, the Fourier transform of that guy, c dagger k up, c dagger minus k down. Sometimes this is called the Thouless form. And a Pfaffian is nothing else than taking this pair wave function and projecting it to a fixed particle number, which is a mess, but it is something like this. So it's a wave function made of pairs of electrons, right, which is anti-symmetrized with respect to all electrons, as it should be, and parameterized by these amplitudes f, which are now not single electron entries, but pairs of electrons. And this is a more expressive and bigger class of wave function than Slater determinants. A Slater determinant can always be expressed as a Pfaffian, just putting some elements to 0, the same way that the BCS wave function is also a wave function for the normal state when there is no pairing. Okay, so it's a very natural framework for superconducting states. So we apply this idea of hidden fermions to the Pfaffian form. And this is done by enlarging the Hilbert space, just as before. And hence, we're going to have these pair amplitudes f here to have components in. So now V denotes the physical sector. I'm going to use interchangeably V for visible or for physical. So we have a block of these F amplitudes, visible, visible, hidden, hidden, visible, hidden. And you can actually show that this general form can be transformed, and this is done because it makes them more amenable to be parameterized by neural networks as a Jastrow factor, which depends on the configuration of the physical fermions, times a Pfaffian of these quantities. So this notation here, n star f star n, means that we take the lookup table of the f amplitude, and we slice this lookup table according to the Fock state occupancies of the physical fermions. So we look at which of the states are occupied, and that's specified by my Fock state n, and we slice the matrix F according to n. And because it's a two-fermion thing, there is two slicing by n and n. Okay, so now, say that again? Is there a limit that this gives you a normal state with no pair? Yes, yes, absolutely. Any Slater determinant, just to illustrate the thing, any Slater determinant can be put in the form of a Pfaffian by, replicating it's a bit more costly, of course, but by replicating the matrix and putting an antisymmetric structure properly. Okay, so the boxes in red here are the boxes that are the terms in this quantity, in this Pfaffian, that we're going to represent as neural networks. And the other ones, FVV and FHH, are going to be optimized as independent amplitudes. So this means that the red things depend on the configuration of your physical fermions, while those guys are amplitudes that are independently optimized of the configuration. Okay, so there are several advantages to this architecture, and I have to credit Ao Shen and Chris for realizing all these very important technical aspects. One of these important technical things is that because the Pfaffian architecture, the Pfaffian structure involves difference of coordinates of electrons, it becomes much easier to implement symmetries, especially translational symmetries, in this framework. So one can use convolutional neural networks to parameterize these red boxes, or if you have a state that violates translation symmetry, which is of course what we want to do with stripes, you can implement translational symmetry up to a certain unit cell that you choose yourself. And you can also use group convolutional neural networks to implement the point group symmetries inside the unit cell. More technical details will be a little bit above my pay grade, but I'm happy to try to answer if there are questions. So this is the equation here, which is repeated on that slide. And this is sort of a cartoonesque picture of what is really done. So this is an example that has two visible fermions and two hidden fermions, just a toy example. Hence, the Fock state has 4 boxes. This configuration is fed at the input of a convolutional neural network, which has different channels. One of the channels produces the justron. Another channel produces the amplitude FVH. This is all processed according to and implemented with a filter to implement the sublattice symmetries. And then this is all collected. This guy goes into the justron. This guy goes into the FVH. And that gives us our amplitude psi. Okay, so this is the general framework. Just a few details, very important details about symmetries, optimization, and cost. As I mentioned, translational symmetry or translational symmetry up to a given unit cell or superlattice are naturally implemented with CNN or GCNNs. Phases with broken translation invariants, we use larger unit cell. And importantly, the precise choice of the blocks that we use in this parametrization were such that we can easily apply low rank updates method for optimizing the Pfaffian, which brings the computational cost from n cubed to n squared. So this is a little comparison here of the scaling of the method as a function of the number of particles for one forward pass of the VMC optimization, and then for the full VMC. This is, for example, neural network backflow from this early paper by Dido and Brian Clark. Basically, if you don't implement sublattice symmetries and you don't do low rank updates, which is also something that we are not always doing in the HFDS framework, this would scale like n to the 5. By going to these hidden fermion Pfaffians, naturally implementing symmetries with GCNNs, and doing low rank updates of the Pfaffian, you can scale this back to n to the cube. Yes? Can you speak louder?
Yeah, what happens if you don't enforce any symmetries? Does it converge to the... Yeah, I will speak louder. So I'm asking what happens if you don't enforce any translation symmetry. So does it converge to a translation symmetric solution then, or why?
That's a good question. Well, first of all, this is yes. I think the answer is yes, but the optimization without enforcing any symmetry is a mess. And I think this is well, correct me if I'm wrong, but I think this is kind of a general rule with NQS, right? Okay, so
Quick question.
Good. Yes.
Yeah, so these scaling considerations might imply that I should just use the hidden Fermion Pfaffian, even for non-superconducting states.
Yes.
Yeah. So,
Well, yes, I think this is correct. I mean, of course, in practice, optimizing a Pfaffian is a bit more expensive than optimizing a determinant. So, but I believe this is correct, that this is actually a good way to go at the normal. I mean, that's what we do in practice, right? As you will see, we also stabilize normal states, obviously.
okay.
Yeah. In fact, this is an important point I want to elaborate, if you allow me, I want to elaborate a little bit on. When we train the system, right, we start from a mean field initializations of the whole machine, right? And where you're going to end up may depend on how you've initialized the wave function. Of course, if you would find a different optimum for each different initialization, that would be a disaster, right? But what I mean is that if you start from a mean field initialization without pairing, you may end up in some local minimum of the energy, right? And if you start the optimization with pairing, you may end up in a slightly different local minimum. Sometimes we end up in the same, sometimes we end up into a slightly different minimum, which allows to stabilize not only when there is a superconducting ground state, but also the parent normal state, right? And of course, what you have to do is very carefully check that even though you ended into different local minima, the local minima you ended up is independent of the amplitude of the mean field wave function you used to initialize, right? So it's not like there is a zillion of local minima, there is a few that you can find. Okay. I don't know if that answers your question to some extent.
That makes sense.
Okay?
I also just have another question. Earlier you commented that the hidden fermions, so your determinant wave function should in principle be able to describe the superconducting state. Is that a matter of practice? Is that
That's coming.
Oh, okay, all right.
That's coming. Now come the results. Okay, so the first thing I'm going to show you as a matter of results is a few benchmarks, because I really think that in this field, being precise about benchmark comparisons is really important. And here are a few examples. So we start with a, say, toy model, which is just 4x4 Hubbard model at around quarter filling. And what you see here is the relative error on the energy. So, of course, we can do ED for 16 sites. So that's a good benchmark. The relative error of energy is defined in this way. So this is the energy we find minus the ED ground state energy, normalized to the energy of the infinite temperature state minus the ground state energy from ED. And you see this is a determinant state with a restricted Boltzmann machine from, say, the older papers from Yusuke Nomura 10 years ago. This is our old school hidden Fermion determinantal scale state, which brought their relative error to about 10 to the minus 4. And with the hidden Fermion Pfaffian state, we go down to less than 10 to the minus 6. So I guess that partly answers your question, okay? So this is good. So 10 to the minus 6 for this very simple benchmark example. This is a slightly more interesting case, which is actually also answering your question, which is, can we actually find superconductivity, right? So, of course, the way to test this is to look at negative U. And what we plot here, so, of course, for negative U, one can do determinantal Monte Carlo, right, because it's sign-free. And here what is plotted is the pair-pair correlation. So this is on 64 sites, 8 by 8. And periodic boundary conditions are, this is something I should have mentioned too, which is that we use PBC. So everything is done on the torus. So this is the pair-pair correlation function for negative U as a function of distance. So the longest distance would be 4, right? Because it's 8 divided by 2. And this is for U equal minus 2. And what is compared here is the DQMC pair-pair correlation function versus our HFPS optimized wave function. So you see that the agreement is excellent. And here we also compare this to the BCS ansatz. So you see that the BCS ansatz moderate coupling is not too bad. But when you go to stronger coupling, where you go more into the BEC condensation regime of that model, then of course the BCS is not good anymore, but the HFPS captures this nice plateau from which we can extract the order parameter, and the agreement with DQMC is still very good. So that answers the question. In practice, we can find nice superconducting states, and this is the pair-pair correlation function at the longer distance, which is a proxy for the square of the order parameter versus interaction nu, comparison to DQMC, and of course BCS as a mean field at large U overestimates that pairing. Okay, so this is negative U. Let's move to other things. This is benchmark number 3. We want to see that we can get the half field Mott insulating antiferromagnetic case properly. Again, something where in that case I think in that case, Monte Carlo would be exact because this is half filling, and this is a comparison between hidden fermions and various other architectures of neural quantum states. And here, of course, the benchmark is AFQMC, because AFQMC would be exact in that case. And you see the relative error of energy at large U is on the order of a few 10 to the minus 5.
Much better than the determinant or not being selected.
Let me go back. Yes, the hidden fermion determinantal state. But, you know, maybe this is not a completely fair comparison because the HFDS was not. I'm not sure whether this HFDS curve that we've used here implements the low rank updates or not. But, you know, it's definitely higher by orders of magnitude. Okay, tougher benchmark, stripes at 1.8 doping. So this is, again, the 4 times L tori. So this is why on this plot there is no comparison to DMRG because we do not do open boundary condition of the cylinder, right? We have to use PBC, making the system, if you want, a bit more two-dimensional, even though this is an elongated geometry. So this is a comparison at very small size with ED, that's the 4x4 we've seen before, and then comparison of HFPS with different other available neural network methods. This is the recent transformer neural network backflow here from the ByteDance group, the Beijing ByteDance group. Okay, from this paper. Okay, so now the real thing, and it's about time. You want to know something about superconductivity in the Hubbard model. So, the repulsive Hubbard model. So what I'm going to show you are our most recent results on how, if I take 1.8 doping and turn on a T prime, whether one can induce superconductivity or not. So this is again the cartoon. We start from this state of fully filled stripes, right, with one hole per site in the stripes, so presumably an insulating state. We turn on a negative T prime, or if you want, this is hole doped, negative T prime. So this is the case sort of relevant qualitatively for cuprates that Chiwei and his colleagues have studied extensively. And we ask, do you get superconductivity? And this is 256 sites, perhaps not this plot, but what we can do is we've run simulations up to 256. And so here is the plot. This column is T prime equals 0. The first line is the pair-pair D-wave correlator as a function of space. And this one is the spin-spin correlator. And if you don't like color plots, you have a comparison here between the spin-spin and the charge, again, half the wavelength, etc., in both cases. So this is T prime equals 0, T prime equal minus 0.3. And I think you see with your naked eye two things. One thing is that for T prime equals 0, the pair-pair correlator becomes extremely small at large distance, while here at large distance, there is a clear non-zero value on the edge of the system for the pair-pair D-wave correlator. And the other thing you see with your naked eye is that the periodicity of the stripe has changed from period 8 here for the charge density wave to period 4 here, at least on the cluster on the finite size system we looked at. And if you don't like to judge things just by colors, which is actually my case, you can plot these things. And this comes back to the thing I was mentioning before. This is actually stabilizing different states with initializing the optimization with different initial mean field Pfaffians, but of course checking that we always go to the same place independent of the amplitude of the optimization of the initial state. And this is comparing three things: the fully filled stripe, which is the yellow thing. This is, I think, at T prime equal minus 0.3. So you see that this is a log lean plot of the pair-pair D-wave correlation. So this state has no pairing. And then this is this half-field stripe, so period 4 charge density wave plus superconductivity, which has a nice plateau as we go to long distances in the system, right? This is actually stabilizing a normal state, stabilizing a half-field stripe with no pairing, right, in which this wiggly stuff is partly due to the fact that the free fermion pair-pair correlation has lots of oscillations when you actually plot it on a finite size system. This is a plot that shows how you can extract a value of the order parameter, which is the square root of this, as a function of, say, the size of the system. We only have 3 sizes on this plot. Why do we have 3 sizes? Because we pick a cluster size which is compatible with period 8 stripes. So we can only do 64, 128, and 256, and more is above our what is reasonable to spend. I'll give you some estimates of the GPU cost of this, but you see that, okay, as you can, insofar as you can judge from 3 points, the finite size behavior of this is somewhat reassuring. Okay, so if you want to know a little bit more, this is how the energies cross as a function of T prime, because obviously this half-field stripe plus superconductivity has to cross the fully filled stripes non-superconducting at some point as a function of T prime, and this is this crossing of energy which takes place around T prime equal minus 0.1, and if you are interested in the energies of these different states on a 256 side system, they are listed here. By the way, none of these things on superconductivity are published yet, and this is going to be a paper, I hope, in a few weeks.
What about the other side of T prime?
Good question. You will understand why I don't have an answer when I show you the GPU cost of these things. But we will at some point. This is the yes, we've been careful about that. This is the correct sign for the whole cube brains. Okay, so importantly, I want to point out that it's in very good agreement, qualitative and even semi-quantitative, with the beautiful recent work of Shiwei, Steve White, Uli, and their co-workers, which indeed convincingly showed that when you turn on a negative T prime, you get superconductivity coexisting with these partially filled stripes, so we can call this a stripy superconductor. Computational cost, that's not an answer to Subir's question, but that still gives you a little bit of an idea. Well, these are the cost on an H100 GPU for the smaller systems I showed before. So this is in the 100 of GPU hours. But for the larger system with repulsive U, the total optimization time, including the VMC, is in the several hundred and perhaps 1,000 GPU hours. So this comes at a cost, despite the efforts to actually change the overall scaling with the various tricks I sort of briefly described. And you see this is not only words. I mean, here you see some scaling of the system tested on different lattice sizes from small to large, comparing, no low rank update, no sublattice symmetries implemented, to full low rank update and 4x4 sublattice symmetry implemented, where we can convincingly find that one goes from n to the 4 to n square, bringing the computational time down by several orders of magnitude. Okay, I was going to tell you a few things about a previous project we did, but this is just going to be advertising because I'm running out of time, with Chloe Govindiai when she did an internship at CCQ, and Joy and Javier. We actually looked at a fun model, which is a fully connected Hubbard model with random hopping amplitude. This model is nice in 2 ways. First of all, it has a mode transition at a critical U, between a small u metallic state and a large u insulating state, multi-insulating state without any magnetic order. The ground state is a total spin singlet. That's one nice thing. So it's the pristine Mott transition. It's also, if you want, some sort of precursor to SYK without the random exchange. But the normal state is a Fermi liquid in that case. And the second nice thing is that this model is exactly solved by dynamical mean field theory in the thermodynamic limit. So that provides a comparison. And this work also sort of provides for the first time, and this is a little bit idiosyncratic, a wave function corresponding to dynamical mean field theory. So that's what we did in this work. We documented that the neural, this was HFDS, the old school way, and we can see the Mott metal insulator transition. The comparison is between the neural network and the plane lines are the thermodynamic limit, dynamical mean field theory, exact solution. And this is the wave function of the MFT, which I've been waiting for many years. So that was kind of a fun project. And by the way, it also shows that models that by construction have volume law entanglement, because this is fully connected, right? So this definitely have volume law entanglement, can be addressed with neural network quantum states. In fact, it's relatively easy to beat DMRG on this model, which is, of course, quite the opposite of what DMRG can do, but Joey Tyndall managed still to do 32-side DMRG with crazy bond dimensions. Anyway, conclusions, perspectives. So I hope I convinced you that hidden Fermion Pfaffian state is at least the state-of-the-art implementation of fermionic neural quantum states, that it allows you to implement symmetries and obtain accurate energies. And at strong coupling, this method supports and confirms the fact that the whole doped Hubbard model is a striped D-wave superconductors upon turning on T prime with another parameter which is about 10 to the minus 2 times the hopping amplitude. So you can call this a high TC superconductor. And we are currently working on clarifying the situation at smaller u and larger doping with and without T prime. And to obey the marching order of Subir, we'll even change the sign at some point. Okay, shameless advertising. This is just one of the many strands of research which is done at the Center for Computational Quantum Physics of the Flatiron Institute. There is actually 2 parallel efforts on a fermionic neural quantum state. Shiwei later today is going to talk about the other one, which is more neural network backflow and continuous space. We do many, many other things. And if you are interested, we have positions available. If you apply in the coming days, you can still apply for postdoc positions. And we're going to have several faculty openings, which are already posted, at least 3 and perhaps 4, which are listed here. Thank you.
Thanks for the excellent talk. I just wanted to, well, maybe before I ask my question, I'll first ask a quick question, which is, just to be clear, in the enlarged Hilbert space, you have a single Slater determinant?
Or Pfaffian.
Yeah. Or Pfaffian.
Yes.
Okay, so then my question would be, is there some established trade-off between the number of determinants or Pfaffian terms that you would use in the conventional approaches and the number of hidden fermions? Is that
okay? Excellent question. Yeah.
Maybe is there a relationship between the amount of correlation you want to get in a state and the number of hidden fermions you can use, or is it more unclear of a relationship?
Yeah, that's a very, very good question. So actually, that's the one thing I sort of hid under the carpet during the talk. I didn't tell you how many hidden fermions we are using, right? So all the calculations here are done with a modest amount of hidden fermions of the order of 12 or something like this. Okay.
Like for size, what?
Independently of size.
Okay.
So in the first PNAS paper with Javier, we actually have a plot which shows how the accuracy of energy depends on the number of hidden fermions, which is fixed, right? I mean, this is a parameter of that you choose. And the convergence was reasonably good. And of course, as you put more hidden fermions, you have a better accuracy and better expressivity. Now, on the fundamental side of your question, we have some formal proofs that if the number of hidden fermions becomes large, the wave function becomes arbitrarily expressive. But besides this formal proof, which is not very useful, we don't have like numbers. I can't tell you to reach that degree of entanglement, we need that value of n tilde. We have no result like that. I would love to have that, but that sounds tough.
Yeah, I have a question. So it seems like in your first or second slide, you mentioned that the number of hidden fermions is the number of configuration of the electrons. But then later on,
No. The number of hidden fermions is fixed. Okay, there are two things. There is the number of hidden fermions and the Hilbert space in which these hidden fermions live, right? And so the number of hidden fermions is a number that we fix. It's not related to the number of the electrons.
I see.
Right.
So that's why you can use it as a hyperparameter.
Yeah.
And the second question is that for the fully connected model, like, obviously you don't have the translational symmetry, but is there any?
Well, it's a model with quench disorder, right? So we certainly don't have translational symmetry.
Is there anything that you can take advantage of?
Yeah, I'm pretty sure that if we were actually, I mean, in this PRL, on this fully connected Fern model, with the old school hidden fermion determinants, we were able to do up to 48 sites, right? It's not quite enough to resolve details of the metal-incident transition in this system. It's enough to find the transition, but to resolve some fine details we can discuss offline. It was not quite enough. I'm sure that with some more work, one could do bigger systems. I'm not sure there is a huge motivation for that specific model because we know the exact solution in the thermodynamic limit anyhow. Exact, I mean, with DMFT, solving DMFT equations numerically. But yeah, I'm sure one can do better. But of course, all the machinery that Chris and Aoshen, heroically implemented, translation symmetry and all this is not geared at that model, which doesn't have. Yeah. Yes.
Were they always compatible with expected metastable states in the system, or are you afraid that some of them might be hallucinations?
I'm afraid of lots of things. Yes, we should all be afraid of lots of things. So we choose superlattice translations, right? So we are not exploring, as far as I know at least, we are not exploring all possible patterns of translational symmetry breaking. And when you go to different fillings, well, there are many works by Chiu and coworkers that have shown how delicate the competitions between the different stripe states with different periodicities, with energy differences that are minute. I'm not sure I want really to go there, but this is going to happen. I mean, if we initialize at different fillings, this is why we focused on 1.8 for the moment, because there, things are fairly well established. But if you go to other filling, you'll have to worry about these things if you want to really assess the competition with stripes. So the local minima are good in the sense that we can say this is the parent normal state, but you have to be careful that the local minima you find is actually independent of the amplitudes of the pairing of the various mean field parameters you put in your initialization, otherwise, right?
But for simpler systems where you don't expect such a rich phase diagram, do you still see local minima or regardless of architecture?
No, actually, it's a good question. At smaller U, we don't. And even, in fact, at smaller U, we don't. And in fact, at smaller U, We can even stabilize superconducting state when initializing the wave function with no pairing. So that's reassuring.
Just a question about your optimization strategy. I noticed on the slide where you talked about the computational resources that you usually only had a few thousand, 1,000 or 2,000 optimization steps. So like that's small in comparison to what people do for like Fermion, for example, where you might have hundreds of thousands of optimization steps.
Right.
So like what, is that just it worked, or do you have?
Well, I mean, we monitor, as everybody does, right? Yeah. We monitor the variational energy and we stop the calculations when we think the thing is reasonably converged and when we think our budget is getting close to being exhausted. Yeah, I'm sure one could do better. If you want some more details, you should contact Chris Roth because he's really the guy who's doing these calculations.
Okay.
So we start with general linear Hamiltonian. If you consider BCS ground state, actually there's no conserved particle number. And
there's no what?
No conserved particle number.
In what?
In BCS solution.
Yes, that's right.
And we try to project into fixed number of particles.
Well, we don't try, we project.
So I wonder if
I mean, this is all at fixed particle number, obviously, right?
I understand, but when we try to solve the bilinear Hamiltonian, we solve the projecting Hamiltonian, and then we do projection. This step is kind of like nonlinear. Are we throwing away anything?
Well, this is why you need to do it computationally, right?
Yeah.
You can't optimize analytically a fixed particle number BCS wave function. Right. It is a nonlinear equation. Yeah. But maybe I'm not getting what.
My question is just will we do this projection to fix the particle number sector?
We do.
Anything, or it's just a good approximation?
I'm not sure I understand the question. I mean, is the question okay? So the optimization, say, of a mean field BCS wave function at fixed particle number, projector non-fixed particle number is, as you say, a problem that cannot be handled analytically. Well, I mean, we hope the optimization does it well. That's that.
Maybe there's questions? Yes.
So probably I've missed this, but like, so we have like a lot of comparisons, like to like, I don't know, paths, like sort of.
Yes, I like doing that.
Yeah, this is great. And then I wonder for superconductivity, like, do you have any similar thoughts? Because like you mentioned that there was like a separate DMRG work on this. Like, do you know like what kind of?
Okay. So for negative U, superconductivity, I showed you all these comparisons. For positive U, the reason we don't compare with DMRG is because the geometries that DMRG can do are not the ones we do, right? So DMRG does tubes with periodic boundary condition on a small direction, not on the big direction. The whole idea of the project was to use convolutional neural nets to implement translational invariance, so we have a toric geometry. So even if we do a calculation on an elongated torus with a small radius, we can do qualitative comparisons, but we can't compare the energy because that, right? And by the way, I'm pretty certain that whether it's a torus, but especially cylinder with open boundary condition and small transverse radius, favors charge density waves. So I'm suspicious of computations that only involve these elongated quasi-1D geometries. That's why in the paper with Shiwei, the FQMC part was really important.
Let's thank Antoine.
Thank you.